exercise on preservation of limits. So let me recall one more time. Definition: a functor f from C to D preserves limits of type. Sorry, sometimes I say shape, sometimes I say type. Type J, if and only if whenever we have a limit or universal cone for a diagram from category J to C. The corresponding cone after applying the functor f, let's call it FPJ, applying f is a limit for the diagram after applying functor f. So it's again from J. No, it's it's from J to D. Let me draw a picture so you have a functor from J to C, and this give you a diagram. Then you have a cone, a limit, diagram. After you apply f, if this FL is again a cone, a universal cone, so limit for the diagram f of D, then we say preserves limit. We could write this this way. I don't think we should add inverse limit. It's more general than inverse limit. Arbitrary limit. Okay. I mean, summarize. In short, write this. The example of this would be representable functors. So let me first recall. A a representable functor denoted so this is a covariant torsion from C to set. For some object C, which maps object X to home CX, and the morphisms are by composition. We'll consider only small categories, one whose objects can be considered as a set. The morphisms can be considered as a set too. You can also consider the C up to set. Correspondingly, sorry, I was right, yeah. It's a covariant functor again. Okay, so let's do our exercise for today. Representable functors preserve limits. So first remark that this is not the same thing, or it does not imply the fact you need embedding preserved limits, because you need embedding is not the functor. It's not this functor. Unit embedding is instead of mapping X to a set, it maps X to a functor. That's unit embedding. Okay, while this unit embedding maps X to, for example, this or covariant torsion. While this maps it to a set. What this is to set C up. Okay, so let's prove this. Proof. Start with, let's say in the category C, suppose you have AI, AJ, you have a diagram, right? And then you have universal object. You have universal cone, let's denote by limit. And then now we want to prove that after you apply the home functor, let's say home C, then still this C lim is the universal cone, and so here it's in the category of set. Let me just very quickly sketching the picture. So now we want to prove that for any set S such that the diagram commutes, I want to show that there exists a unique map. The way we do this is that for any small element S here, I'm going to define what is the image of this. So let's see more precisely. Take a small s, suppose this small s is mapped to here, let's say alpha I, alpha j, so it's mapped to alpha I of s here, which means given small s, it gives a map from C to AI, alpha I, and through this, let's call this F through F, composition with F, it maps to alpha J, make diagram commutes. And so in particular, under this precise alpha I, alpha j. By the universal property of limit, there exists a unique, let's call this alpha, from C to lim AI, and I'm mapping this S to exactly to this alpha, and you will check this is indeed making this diagram commutative, because alpha composing with, let's say, what do we have to check? We have to check this alpha from C to lim AI, then map to C to AI, and through this, let's call this beta I. This is mapped, alpha is mapped to beta I alpha. And so the commutative diagram here is telling you that beta I compose alpha equals alpha I. So here is alpha iOS, sorry, alpha iOS, and so it's the same, making the diagram phase, so it's done. So you prove the uniqueness factorization.